I'm going to call on the first speaker, who is Scott Bailey.
I'm very grateful to have gotten this invitation to speak here to you and to speak at a symposium dedicated to Charles Barth. I'm incredibly lucky to get that. There are a lot of people who worked with Charles Barth on many things, especially nitric oxide. So many people could give this talk. It's a privilege that I got to do it. It was a privilege that I got to work with Charles Barth at all. I'm lucky. I spent 20 years, first as a grad student and eventually a colleague, working with Barth on nitric oxide. Many hours talking about this topic. And so I hope I can tell you some of what his thinking was behind certain things. Many people in atmospheric science, when they think of Charles Barth, they automatically think of nitric oxide. He did so much work in that. You're going to see today that he did lots more than just nitric oxide, but he is certainly, within atmospheric science, very much affiliated with this molecule. And I want to show you during this talk some of what he was interested in and why it's important to the community and a little bit of the physics behind it. I want to acknowledge that I had help putting this talk together by a few of my colleagues at Virginia Tech. You're going to hear from them today. Marty Malinczak at Langley. And of course, I'm relaying information that we didn't just come up with, that many of you came up with, many of Barth's students and other colleagues, and Barth himself. In fact, Barth is very much a co-author on this talk. I cheated a little bit because some of the slides and figures I'm going to use to show you, he made, or we made together for presentations we gave during the snowy era that I'll tell you about. So if you start thinking during my talk that, boy, it's a little bit lame, be careful. It's who you're blaming, because it might not have been me who came up with it. In fact, it probably wasn't me. So if you think of the atmosphere and you plot the densities of some of the key species in the atmosphere, you have the major species, nitrogen and oxygen, we all know the atmosphere is made of. And the altitudes where we're working with nitric oxide overlap with the ionosphere, the charged particles in the atmosphere. And you see that in density, the charged particles are much lower, orders of magnitude lower than the neutral density of the atmosphere, the thermosphere. And nitric oxide in log scale is somewhere in between. We would call it a minor species, although it has behavior that's much more like a major species. But it's a small fraction of the number of molecules. In fact, I can show you that. If you plot again the nitric oxide density, has a peak in density near 110 kilometers. But if you plot it in terms of what fraction of the atmosphere those molecules are, the peak is actually much higher, and the percentage is something like 0.04 or 0.03. It can vary, but it's something like that. Something Dr. Barth used to like to say when he introduced nitric oxide was it has about the same abundance in the atmosphere in terms of fraction as CO2 does, and it plays very much the same role as a radiator. So you can think of it that way. It's about 0.04% of the atmosphere at its peak. In terms of why it's important, there are several reasons. It's very interesting that a lot of what I'll say here, why nitric oxide is important, is probably not why Dr. Barth was pursuing it so energetically. I'll show you the things he was interested in. But when we talk about to the atmosphere, why is nitric oxide so important, one of the first things is that when it reacts with ozone, it reacts catalytically, meaning it reacts with ozone, the ozone is destroyed, but the nitric oxide molecule survives the process. And so wherever there are abundances of nitric oxide that meet up with ozone, the ozone is going to suffer for it. The nitric oxide will live. But more than that, in the ionosphere, near 110 kilometers above the ozone layer, nitric oxide is a key part of the lower part of that ionosphere. It's the easiest molecule in that altitude region to ionize, to break an electron away from. And because it's easy in that regard, it becomes what's called the terminal ion. You know, there are other ions there, ionized N2, O2, atomic oxygen, but they'll eventually give up their charge to NO because it's the easiest to ionize. So wherever there are abundances of NO, you'll see lots of NO+, the ionized nitric oxide. Also, as I mentioned before, it behaves sort of the way CO2 does in the lower atmosphere. It radiates. So by radiating that infrared energy, nitric oxide is a way of cooling off the upper atmosphere. It's giving up energy back to space, energy that could have come in any form that led to the creation of nitric oxide. So chemically, in terms of the structure of the atmosphere, controlling the temperature, nitric oxide is very important for all these reasons. And one of the things I'm going to show you is, in addition to all this, it can tell you about what's going on in the rest of the geospace environment. This is an old cartoon I made as a graduate student, but with Barth. In fact, he told me that my presentations were too boring at one time, and I needed more cartoon overviews of some of the things I was doing. So we made this in something like 1992 or 1993. So it might look a little old, but it still gets some use. I'm going to tell you how nitric oxide is produced. In fact, there are several talks today going to talk about NO and its chemistry. But one key element of that physics is what's called a photoelectron. The idea that an electron is created after solar photons break up molecules in the atmosphere or kick an electron off an atom or molecule in the atmosphere. Those electrons are ejected after the ionization process. Many of them carry off a lot of energy. And that energy that's carried off with the electron, when it reacts with some other species in the atmosphere, say N2 or O2 or O, when the electron impacts it, that extra kinetic energy that it has can ionize itself. It can ionize, again, N2, O2, or O, or it can dissociate a molecule, or it can excite an atom or molecule. Right? That energy that the electron carries off is important. It can do more things to the atmosphere. And that's the way that the solar photons, their impact is enhanced by the photoelectrons. And these are very important to the NO chemistry. It's also important to note that these were first theorized, I guess, in the early 60s. They were proven to exist by an experiment by Dr. Barth, where he measured an emission that could only be created by electrons. Oh, wow. I'm not going to go through this. Many of you who've worked with Dr. Barth have seen the chemistry of nitric oxide and seen it evolve. You've seen different.
I'm off by 10 minutes. Yeah.
I thought so. I was so worried about that.
Sorry.
That's okay. So that means I get 2 hand signals. Okay. So now that he's got me worried, I'm not going to go through the details of all this chemistry, right? And I probably shouldn't anyway. But it is good nostalgia, and you're probably going to see early versions of this. Some of you had versions of this in your dissertations. People I'm looking out into the audience. It's evolved. This one was put together a couple years ago by Justin Yonker. There's a few additions from your days. But, some of the key things are to note, and I apologize, I can't shine on both screens, but down in the lower right corner you see atomic nitrogen in the form of N-double-D or N-quartet-S, N and 2 Ds and N4S. Those are nitrogen atoms, but the doublet D is in an excited state, whereas the quarter S is in a ground state. So the N-double-D has a little extra energy. And so it much more efficiently, when it reacts with molecular oxygen, creates nitric oxide. And that's one of the key things to see. It's the N-double-D reacting with oxygen to make NO. The real question is, where do you get the excited atomic nitrogen, right? And that's processes that start with ionization. The ionization that creates the electrons. They go off and impact N2. That makes N2 plus. N2 plus can react with O to make N-double-D. And there are other processes. You can say that what's really important is that energy in this form of solar photons and photoelectrons breaks up the N2 molecule that eventually allows nitric oxide to be formed. It's a little more complex than that, because it turns out what's really important is the ionization, not so much the dissociation. The reason that's true is that this N-quartet-S, the ground state atomic nitrogen, is actually better at destroying nitric oxide than it is at creating it. It takes a high temperature for N-quartet-S to react with O2 and make nitric oxide, but it very efficiently destroys nitric oxide. So the breaking up of the N2 molecule both creates nitric oxide and destroys it. Ultimately, it's the ionization that's the most important for production. I won't go through these in detail. These are just altitude profiles that show these processes at work. Again, the processes that most make nitric oxide are atomic nitrogen reacting with O2. At high altitudes, the N-quartet-S is an efficient producer of nitric oxide, but mostly it's the N-double-D, the excited. The loss of nitric oxide is predominantly the process up top, reaction with N-quartet-S. And again, how do you make that N-quartet-S? That's solar energy ultimately as well. And again, where does the N-double-D, the excited atomic nitrogen, come from? You see several processes there, but the ones in blue, it's interesting, it's the NO plus and the N2 plus that lead to the formation of N-double-D. So it's very important to understand, why do we have nitric oxide? It's because we have the ionosphere. Now, we'll get a little more into some of the physics, but how do we know everything we know about nitric oxide? It's a lot of chemical studies, it's a lot of lab observations, but one of the things Dr. Barth excelled at, as we all know, is observation from space. okay? And he did several experiments to measure nitric oxide from space. I'm going to focus on one of them because it's near and dear to my heart, and I would argue it was very near and dear to his heart, and that's the SNOWY mission. Pictured here is the SNOWY satellite. It's a very unique mission. Spent 7 years, a little less than that, in space. Had a measurement, maybe fairly simple by today's standards, but it measured altitude profiles of nitric oxide. It's very much like an experiment on SME. In fact, it used some of the SME hardware we put on it. But it was special in a sense, well, for many reasons, but it's very true to say that to a large degree, SNOWY was built by students under the leadership of Charles Barth in a very visionary program called STEADY, the Student Explorer Demonstration Initiative, that was championed by a colleague of Charles Barth's. I'm spacing his name, I knew it just 1 minute ago, but Paul Coleman. And maybe Charles Barth suggested it to Paul Coleman. We all thought that, but Dr. Barth never told us. But they decided that you could make space missions a whole lot cheaper and a whole lot more educational to the people building them if you let students do the majority of the work. I don't want to say we didn't have professionals. We had a lot of key professionals, say 10 or 12 that worked nearly full time on SNOWY. But we had 110 students that worked on SNOWY, and they did a lot of the work. And this was the first time LASP built an entire satellite within LASP's building, and did it predominantly with students. And SNOWY did a lot of things. Scientific highlights are listed here. We measured nitric oxide. As I said, it's the sun and solar photons that ultimately create the nitric oxide, or it could be particles from the sun. We measured the solar photons as well. We had an X-ray experiment on there. We also had an auroral experiment on there to look at air glow from energetic particles. We quantified the relationship between the energy inputs and the nitric oxide. We got a nearly 7-year database of nitric oxide that still today stands as the preeminent database for everybody to look at. We learned things about the magnetosphere by looking at nitric oxide, the geomagnetic energy that comes in and powers the atmosphere. And also, I think Amy's here somewhere, did a lot with polar mesospheric clouds, much like SME did before that. 42 publications. I think I have that number there. That was verified. I had somebody double check me on that. 42 publications from the one experiment. 11 different institutions. People still today are using the data. I know for a fact that papers using SNOWY data are going to come out real soon, so we're still going. The years it flew were 1998 to 2003, and we're still trucking, I think, with no end in sight. I'll show you later that some studies are going on with nitric oxide that are going to make it even more usable for people. But cannot avoid mentioning the 110 students, and I'll talk to them more at lunch, but what they gained from that experiment and the leadership of Charles Barth and the experience, and really what the professionals learned. The professionals who worked on SNOWY had not built a spacecraft before, right? They were used to UV instruments. So we did the whole thing here. Everybody benefited from that. I think the lab is a different place, in part because of SNOWY. I think that people are different. The 110 students, look at what careers they've gone on to. Some of them are in this room. Some of them have leadership roles in this lab. Some of them have leadership roles across the country. It's phenomenal what that did for people, and that can't be underestimated. And that's one of the true legacies of Charles Barth. But to get into some of the science, the idea of SNOWY was to relate nitric oxide to the energy inputs, and here I show altitude profiles for low, mid, and high levels of solar irradiance. So the soft X-rays that create nitric oxide, you see it responding to solar X-rays. Just like photoelectrons lead to production of NO, geomagnetic energy in the form of auroral electrons also create NO, and you see for different levels of geomagnetic energy, you see the NO responding. Take a look at the x-axis there. It's much different on the right side. The geomagnetic energy leads to much larger levels of nitric oxide. You see the highest amount of NO at the poles and the most variability. Once Dr. Barth had this database, and Justin will tell you the history of NO later, and Barth was very interested in the relationship between solar soft X-rays, the solar photons that create NO, and the NO itself. But once we had that measurement of the NO, and we had a model of the NO that many of the people in the room as students helped Dr. Barth create, that related solar energy input to NO altitude profiles. Once he had that, he quickly showed that he could use the theory of NO with the measured energy inputs to reproduce the observed NO. And you see that here. This is from our 1D photochemical. We call it NOx 1D for the students who remember this evolution. And the snowy data in red. Very quickly, we got that agreement. And so let me tell you what he did next. After he had the agreement in the low latitude region with the soft X-rays. This figure right here, myself, Ken Mankoff, and Dr. Barth made this. I think I can argue it's one of my favorite figures of my career, and I think I can make the case that it was one of Charles Barth's favorite figures of his career. Because many of you may know that this figure, he made a big poster of it, and he sat it outside his office, and it sat there for years. And over the course of years, I remember us wheeling our chairs out of his office to sit in the hallway next to it and talk about what we saw in here. And there's a lot of physics sitting in this figure. So what he did was, these are the snowy observations up top. That's latitude, and the x-axis is time, and brightness tells you how much NO was at that latitude at that time. So these are daily averages. This is all 106 kilometers. And you can see that the NO is very variable. You see at the high latitudes, the red curves, you see a lot of NO. When you get to the equator, it's a lot less. And you can see the seasonal variation, what you see in the winter to the summer. The snowy needed sunlight to measure NO. That's why you see these dark spots in different regions. So we could observe when there was no NO in the polar night. And what he did was, when Barth became good at using the model to generate the solar photon-induced nitric oxide, he ran the model for all the locations and subtracted off all the NO that was created by solar photons, leaving at the bottom all the NO that's created by auroral energy, solar energetic particles, aurora. And when you look at that, there's a lot of amazing things in there. First and foremost, you see these dark regions that are all in summertime for every season, right? In the summertime, there's not much NO created by geomagnetic energy. In the wintertime, very large amounts of auroral-induced nitric oxide. You look at the equator, sometimes the aurorally produced NO reaches all the way down to the equator. Now that's not actual aurora at those latitudes, right? We theorized at the time that what was happening is the NO is created at high latitudes, but the effect of the aurora is so strong to generate winds that carry that NO downward. And we thought that was a great theory until a guy named Phil Richards came along, right? And suggested we need to think about that a little more. It turns out that there is wind, but what it's carrying is heat, not nitric oxide. And the heat that it carries makes the formation of nitric oxide by solar soft X-rays more efficient than it would have been otherwise. That was the problem that Dr. Barth worked on near the end of his career. His last two papers on nitric oxide were all about how that heat transport, called joule heating, created nitric oxide at low latitudes. So it's true that once he made this figure, at least with regard to NO and the atmosphere, he never stopped understanding it. Right? Other things you see in here at the beginning of the season, you make more NO than the later part of the season. That's an effect that he thought was O2. We never got to finish that, but he saw it. And there's many more things he saw in this figure. Literally years we spent looking at this, learning from it, and writing papers on different aspects of it. Just one of the cool things we learned about the magnetosphere, and Dan, we worked together on this. If you use the nitric oxide to give you an estimate, by iterating with the model, an estimate of how much auroral energy must have been in a location, and you average that over all the equinox periods, you would expect that the aurora doesn't favor longitudes, that it deposits its energy equally at all longitudes, especially when you average over a long time period. It's not true. No matter how we average it, there was always this longitude region that saw more effects of auroral energy than the other longitude regions, and it's just to the west of the South Atlantic anomaly. And so Dan Baker would be much better to explain this than I would, but that told us about the particle populations that are responsible for the aurora and how some of them are depleted near the South Atlantic anomaly. And so you saw a reduction in those regions, and outside that region you saw enhancements in the particle effects. And it told us that this is most likely particles that are bouncing back and forth from high latitude to low latitude. Definitely I'll let Dan explain this in the future. Just to show you that we still are working on nitric oxide, still learning it. There's a figure that Justin Yonker produced even just recently. Whereas we had used the 1D photochemical model that all us grad students worked on for so long, now we're moving into the 3D world. And Dr. Barth started this, his 2010 and 2009 papers were using 3D models to study NO. Justin is putting new things we learned about the chemistry into those models and applying it, and I won't go through in detail what all he's doing, but if you look at the red curve, which is the updated model with his chemistry, compared to the blue curve, which is the old, he's improved it quite a bit. right? The modern global models are doing much better at resolving NO, and it's snowy that he's comparing to in each case. So more work with snowy. I told you that NO is a good radiator of energy. You're going to hear that in a couple talks today, Karthik and Jeremy Winter. This is an experiment called SABRE, which measures the radiation, not the nitric oxide density, but the radiation from nitric oxide. For the last 13 years, I think they're up to. And again, you see all the solar variability that's nitric oxide is responding to, and the cooling responds to it as well. And I'll let those guys finish that off. A very new application for nitric oxide, or a new role that we've learned nitric oxide is playing, is we've learned in recent years, whereas the nitric oxide that Dr. Barth studied was predominantly up high, up near 110 kilometers, that sometimes that nitric oxide gets pulled down. This is from an experiment called SOFI on a satellite that AIM, which was managed out of LASP, and a lot of the instrumentation was built here at LASP. You see different years, different amounts. Sometimes the NO goes all the way down to 40 kilometers. And it's responding to changes in the vertical winds that are triggered by what's called a sudden stratospheric sudden warming, a warming event in the stratosphere that changes the meteorology and allows nitric oxide to be pulled down. And just to give you a sort of an up-close version of that, here's the NO being pulled down. It takes a couple of months. I seem to have lost my dates on there, but it takes about a month for that to get down. And the NO that would normally be up in the lower thermosphere, 100 kilometers, works its way all the way down to 40. And that's going to have a significant impact on ozone. All that's been observed. This type of science has been championed here at LASP by Cora Randall, and this is going to lead, we think, to new space missions, because this is an important thing to study. This is solar energy coupling to the thermosphere to create the NO, coupling to the stratosphere to destroy ozone, right? This is space science coupling with atmospheric science. And to study that, we have a rocket experiment that's out at Virginia Tech. Bill McClintock is a huge helper in this. We launched it in 2011. The real point I wanted to make with it, it's hard to recognize from this picture. This was the best picture I could show that had the rocket, but also had this particular skin. Many of you who've been coming to LASP over the years might remember that for a while one of Dr. Barth's rocket payloads was hanging from the ceiling out of that atrium. Does that look familiar to everybody? It's not there now. It's right there. Right out of Virginia Tech. So, and Dr. Barth was a helper in this rocket experiment. It flew in 2011. It's going to fly again in January. It's got a spectrograph that Bill built. But that telescope used to be what's called the planetary payload and hanging out there at front. But it had a big mirror that really helped us for our experiment, because we needed a large collecting area, because we're measuring NO at night in the polar region to study that NO that's being transported down. And to measure at night, you need stellar occultation, championed by a graduate student in here I don't see, Steve Massey, I believe, right? So to do that stellar occultation, we need a big mirror for collecting area, so Barth's planetary payload was the logical choice. And he was sort of happy to give it to us. We took it down, and he was happy to see it being used again, and it flew, and we're going to fly it again. So Dr. Barth is still, at least his equipment, is still studying nitric oxide. And I just want to end by saying there's still plenty going on. You see the SABRE data I showed, you can hear about it from Karthik and Jeremy. This, what I just showed you, the transport of nitric oxide, it's a big deal. The way it shows the heliophysical and atmospheric science coupling. We proposed full missions to study that, and they were very well reviewed, and I think that's going to win, hopefully, in the next selection. The study of nitric oxide is very much alive, and the reason we understand what we do about nitric oxide is because of the work Charles Barth put into it. You're going to hear all about the history from Justin, but he spent his career helping us understand not just nitric oxide, and not just what it does to the atmosphere, but what it can tell us about the atmosphere. That was really how he looked at it, right? First you understand how nitric oxide is produced and destroyed, but once you have that, what is it teaching you? That figure I showed you, he and I spent many hours trying to figure out what that is teaching us, and that's how he viewed nitric oxide. It's teaching you about the energetic processes in the atmosphere, and that legacy is far from gone. It still continues. Thank you to everybody.
So thanks a lot, Scott, and thanks for that talk. Nitric oxide, the upper atmosphere, the current understanding as provided by Charles Barth and colleagues. This talk is now open for questions or comments. Yes,
One
Dave.
of the other things that we discovered with SME.
Dave, would you stand up? Oh,
We discovered with SME is when we saw a large photon event that penetrates into the stratosphere, and we were able to measure its effect, which is the nitric oxide production and its effect on ozone. So I just wanted to bring that in.
Oh, yes, absolutely. I should not say that was a new idea. I made it sound like Sophie was the first to make that
No, I'm not
observation.
saying that. I'm just saying this is a different aspect.
Oh, yeah.
Photons.
I see.
beautiful. Other questions?
So Scott,
Comments?
I'd point out that picture you have of the students who worked on Snowy. Not only have they gone on to do great things scientifically, but I could see at least one marriage in that picture.
I think the answer is 3.
Maybe.
Depending on how you count, if Amy and John count, it's 3. Pete and Heather, and Mike and Christy.
Good.
Super, super. Thank you.